Hey everybody, Mr. Judson here. So our goal for today is to be able to find the continuous rate of decay given some information. Now remember, when we graph a function and we talk about decay, it means there's a certain amount of it to begin with, a certain amount in the beginning, but whatever it is, there's going to be less and less as time goes on. Okay? We've talked about the value of a car, how it depreciates. Okay, but what about things that like fall onto the ground and begin to rot and decay? That's a continuous process, right? And again, anytime we see that word continuous, right away what we want to think of is A equals PE to the RT. Now, our book uses a different formula, but I've never used it. I know what the formula is, I've used it, but I never use it as a teacher. I just always go straight to the PERT formula. Okay? Because if something is changing continuously, which that's what happens when something's rotting in the ground, it's continuously decaying, then we can use this. And they both produce the same answer. And so my feeling is always, why add another formula if one that we have already works? Let's just stick with this one. Okay, that's what we're going to do. So, so usually our book will say something like the half-life of something. All right? I don't know what the half-life of a banana peel is, but if you've ever eaten a banana and you've left the banana peel laying out, it starts to turn brown and it starts to rot and decay really fast. Okay, the moment you peel it off the banana. So I don't know, if I take a banana and throw it in my backyard, what's the half-life? That word half-life means how long is it before half of that banana peel rots and decays into the ground? I have no idea, okay? But let's just say it's 3 days, okay? In 3 days, if I go back and look at that banana peel, half of it has rotted into the ground. So I'm just making this stuff up, all right? If a banana peel has a half-life of 3 days, it takes 3 days for half of a banana peel to rot and decay into the ground. And then the next 3 days, another half of what's left will rot and decay into the ground, okay? So what we want to do is we want to figure out what the rate of decay is for a banana peel. So we want to use this formula, and one of the questions that people often have is, like, how do you even know what you have to begin with and what you have later? Like, how do you even know? And I'm like, it doesn't matter. Whatever you start with, half of it is left after 3 days. Right? Whatever we start with, because this is an initial amount, half of it is left after 3 days. And by doing that, I should be able to solve for R. So pick whatever number you want, okay? I always pick something easy, like, I don't know, 2. Let's just say a banana peel weighs 2 grams. Okay, I have no idea what a banana peel weighs. It's probably more than that, I don't know. But let's just say it's 2, and half of that will be remaining in 3 days. Half of 2 is 1. Okay, I've got e raised to the r times 3 days. Now, the moment I move that 2 over here and divide, 1 divided by 2 is 1/2 or 0.5. So what if somebody would have started with 10? Okay, half of it would be 5. When you move 10 over and divide, you've got 5 over 10, that's 1/2 or 0.5. What if somebody said, I want to start with 20 grams? Okay, half of that's 10. When I move that over and divide, because I have to isolate the base and the exponent, so when I move my 20 over and divide, I've got 10 over 20, that's 1/2 or 0.5. So no matter what you start with in a half-life problem, if this is half of the original amount, once you move it over and divide, it becomes 0.5. There's the half-life. So if you really wanted to pick the best number to start with 1, and half of that is 0.5. right? Because then you don't have to do anything. You're just ready to go. All right, since I started with 2, I need to move that over and divide. And so I've got 0.5 equals e raised to the, we'll call that 3r. Remember, we're trying to find the rate of decay, so r is what we're solving for. So now I'll take the natural log of both sides. I'll bring that 3r down in front. So I get 3r times natural log of e. That's equal to natural log of 0.5. I know that's going to equal 1. So to get r by itself, I just have to divide by 3. So r equals natural log of 0.5 over 3. I always caution people of doing this. You know, you look at this and you go, oh, so a half-life, the rate of decay is just the natural log of 0.5 divided by however long it takes. What we've done is we've developed a formula, which isn't a bad thing, but at some point in time, if we ever have to explain how did you get to that, or I see what you're doing, but why? You know, we don't really know why if we haven't gone through these steps. Okay? If we always start with the PERT formula and plug in what we know and then solve, we know why this works. Once you develop a shortcut, you don't really know why it works. You just know that's what I'm supposed to do. Okay? All right, so now I'm going to grab my calculator and I'm just going to do natural log of 0.5 divided by 3. And there's my rate of decay. So r equals a negative 0.231. Okay, it's negative because it's decaying. We're losing the banana peel. And it's decaying at a rate of 23.1%. That's the rate at which it decays per day. Okay? Whatever our unit of time was here, this was in 3 days. So our daily rate of decay, okay, it's not just at the end of one day. Here's what happens. It's a continual process. Okay? But that is a rate at which it decays per day. Remember, story problems, we always include labels. All right, let's try a different one. All right, virus. Yeah, we all know about viruses right now, don't we? A virus quadruples every 2 hours. I have no idea if this is a realistic problem or not. I just made it up. But they want us to find its growth rate. All right, so I'm expecting an answer larger than 1 this time. Remember, larger than 1 means growth. Between 0 and 1 means decay. All right? So a virus quadruples. It becomes 4 times as much as what it was in a 2-hour period. Okay? When a virus is growing, that's a continuous thing. Continually grows and spreads. So again, we're still using our PERT formula. And so if it quadruples, okay, I got to start with something and it becomes 4 times as much. You know, so again, what's a good starting amount? Make it easy on yourself. Start with 1. Start with 1. So this is going to be 1 and it quadruples to 4. Now if somebody said, well, I want to start with like 15, whatever 15 means for a virus. Well, then you quadruple it and you get 60. Oh, well, I want to start with 2. Okay, fine, quadruple it, it becomes 8. It doesn't matter, because the moment I move this number over and divide, I get 4. All right? Times e, raised to the r, that's what we're trying to figure out, and it took 2 hours for this to happen. So I got to make sure I remember my time frame. This is in hours. It's a growth rate per hour. All right, so multiplying by 1, it doesn't do anything, so I don't even really need to write that down. What I need to do now is take the natural log of both sides. And so what I get, if I bring my exponent down in front, I get 2r times natural log of e equals natural log of 4. We know that's going to equal 1. So to get r by itself, I just need to divide by 2. So r equals natural log of 4 divided by 2. So I go back to my calculator. I do natural log of 4 divided by 2. make sure you get that closed parenthesis on the natural log. Okay, if that's not there, it changes the whole problem. So 0.693. So R equals 0.693. That's our growth rate per hour. Right? So eventually what we want to be able to do, and this is what we'll see on Wednesday, is we want to then be able to take this growth rate and predict how I don't know what this means when you say a virus. How big is the virus after a certain amount of time? How big is it in a week? Well, how many hours are in a week? We'd have to go through and figure that out. Or if I was looking at a banana peel, could I predict how much of that banana peel is left after 2 weeks, 14 days? Okay, but we got to be able to find the rate at which something is growing or decaying first before we can do this. Okay. All right, one last problem. All right, so this is one that we'll see in our book, and it's pretty common when you talk about this stuff. Carbon-14 has a half-life of 5,780 years. Okay, it means it takes 5,780 years for half of this to disappear and decay into the ground. That's what we're saying. Okay, I'm not sure if I've got exactly the right number here, but it's pretty close to this. So what is the rate of decay? Well, same as before. PERT formula. You write this down each time you use it, and it doesn't take long before you got it memorized, right? So half of it disappears. So how much do you want to start with? Well, I'm going to make it easy. I'm going to start with 1 gram, 1 pound, whatever, of carbon. Half of it will be remaining at the end. So just like if I invest money, what do you have at the beginning? What do you have at the end? E is just a number. I'm trying to find the rate, and the amount of time here is 5,780 years. It takes a long time for carbon to dissolve into the ground, okay, or decay into the ground. That's why scientists look at it, is because it sticks around for a while. What did I just see on the internet? I saw uranium, which is what's used to make nuclear weapons. That stuff takes 700 million years for half of it to decay into the ground. That's why it's so dangerous to have that stuff around, is because it doesn't disappear anytime soon. Why do we even make it? Why do we do that in this world? It's a disaster waiting to happen. I can only hope that that doesn't happen to us. That's why you always hear politicians saying we need to have nuclear arms reduction. We need to limit this stuff. We can't destroy our world, right? All right, so let's see. Again, 1 doesn't do anything. So I'm just going to go ahead and erase that. If there's nothing written there, then we know the number in front is a 1. I'm going to take the natural log of both sides. So I'll take natural log of this, natural log of this. And then what I get is natural log of 0.5 equals, if I bring my exponent down in front, I've got 5,780 R times natural log V, which we know that this equals 1. And so to get R by itself, I just have to divide by that. So R equals natural log of 0.5 over 5,780. And so now I'll go to the calculator. Natural log of 0.5 divided by 5,780. Oh, look, I forgot my parenthesis here. Got to make sure to include that. I looked at that and I thought, whoa, that means we're losing a lot of it every year. I started with 1 gram and I'm losing 7, and something's not right. So let me bring that back and get my parenthesis in there. Right there. Second insert and put a parenthesis in. All right. There we go. So yeah, so this is scientific notation, and it's telling us to take the decimal point, move it in the negative direction 4 places. So if I go over 1, I got to add 3 more zeros after that. So R is going to equal, let's see, 278. R is going to equal a negative 0.000278. So my decimal point was right here. I've got to go in the negative direction 4 places. So 1, 2, 3, 4. Okay. So you can see that is a very small rate of decay. Carbon-14 decays very, very slow. And that's why we have this thing called carbon dating, is because scientists use carbon dating as a way to figure out how old something is. They'll see how much carbon is still in it, and because they know it doesn't disappear very fast, once you know that rate of decay, you can use that to predict how old a set of bones are, or if you're digging the ground and you find a chunk of charcoal because there was a forest fire at some point, you can figure out how long ago that forest fire took place. All right? All right, so this is per year. All right, that's it. That's all we have for today, is just finding rates of decay or growth rates of like a bacteria or a virus or fruit flies, something like that. We're just trying to solve for rates of growth or rates of decay. All right, so today's assignment is a worksheet. It's on my Sway page, so if you guys go and look there. All right, so we're starting off assignment number 17, week 17. It's just a worksheet. It's not very long, okay? And you can find that on the classroom website. So if you guys go there, just look for worksheet that says rates of decay or growth. All right, you guys take care, stay safe. I'll see you later. Bye.